Yes, maybe it was a bit imprudent, comment dirais-je, en anglais on dit comment imprudent?
Be careful. No.
Uncareful, uncareful,
That's not
uncareful to choose that because I didn't have the time to really prepare it before this conference, and I had this course to give, so I could not check the things that I wanted to prove, and so so yes, work in progress, and I will be happy to have your opinion about maybe some of the statement or conjectures that I make. Maybe you already know how to prove them, or yeah. So this morning, the last talk by Mike Prest, there was. Prest developed an analogy between topos theory and abelian categories, and so this analogy between abelian categories and topos theory is very much on the mind of many people. And I would like to say a few words about this, not because I have much to say. Actually, I'm presently doing some work with Pierre Cartier on that. And I'm a bit intrigued because I thought that I knew the subject, and the more I think about it, I realize that there are many things that I don't know. Maybe a Bible for the abelian categories is the a thesis of Pierre Gabriel, Des catégories abéliennes. Yes, right. It's really a Bible because, yeah, it had a big impact on. So I don't pretend to understand everything which is in this paper. Oh yes, of course. Tohoku was before. Tohoku 1957 or something. And
in 55, published in 58.
55, 58. The thesis of Gabriel probably was also written before publications, formal publication.
Written in 60 and published in 61, approximately.
Okay, 61, yeah. And in there are many interesting things that I had never observed before. And one of them is the construction of a category from an additive category. Let me give you the construction. So suppose that A is an additive category. By this I mean that you do have direct sums, right? Of course, zero and finite finite sums. Otherwise, I would call that a pre-additive category. And in there is a construction of maybe it could be called, well, I'm going to call it like this, a lex of the left exact completion of an additive category. There are many ways to do the left exact completions of by left exact, I mean that the additive category now has kernel. You don't ask for an abelian category, but just left exact category. I mean an additive category where every map has a kernel, okay? Otherwise, a right exact additive category would be one in which every map has a co-kernel, okay? And the construction is very simple because what you do is that you take the category of arrows of A, and you mod out by an ideal. The notions of ideal make sense in any additive category or even pre-additive category. It's simply for each arm AB, you need to have GAB subgroup, and which is closed under compositions on the left and on the right. So it's a two-sided. It's a two-sided idea.
Or subfactor of the arm functor.
Yes, right. That's a good way to say it. Right. Yes, the arm functor is additive, and we know what is an additive subfunctor of a functor. So J is just a subfunctor of the arm functor. So it's a little bit like saying that a two-sided ideal is a sub-bimodule of the yeah. Okay, so what is this construction? You can describe it like this. Yeah, so you have A0, A1. These are an object of the category of arrows. So a map in the category of arrows is a commutative square like this. So I'm describing arm AB. Arm AB, arm between two arrows, this is the set of all commutative square. Let's say F0, F1. And now the congruence, or JAB, is the set of well, let's say F0, F1 is in GAB. In GAB, if there exists a map H from A1 to B0 such that F1 equal BH. So what you're asking is for a diagonal, but not exactly a diagonal, it's weaker. You just want this triangle to be commutative, A and B. And Gabriel studied this category, and actually he explains where it is coming from. It is actually coming from the constructions of Cartier, which is constructions of the derived category of an abelian category. You see, this is the beginning of a resolution, or maybe of chain complexes. So Cartier would describe the derived category of an abelian category using chain complexes of injective objects, and take homotopy classes of maps between injective objects. And for the homotopy relation, I hope I got it right. That's correct, huh?
The homotopy is decreasing the degree because the differential is.
Yes, yes. Then if you truncate this construction, you get that. So, but this construction seems to be due to Gabriel, but it was inspired. Gabriel says explicitly in his paper that it is inspired by these constructions of Cartier. I was surprised because this is what Pierre told me also. But he told that the idea maybe of a derived category maybe was the beginning of the theory of derived category was you have an important contribution to this.
The next step was to axiomatized triangulated,
Triangulated categories.
the next step.
Right, yes.
which was done by them.
Yeah, yeah, yeah. So the nice thing about this is that this additive category, that's an additive category. You take the quotient, the definition is that you take the quotient by J, by this two-sided ideal. And now this thing has kernel. It's an additive category with kernel, and it's the solutions of a universal problem. In other words, if you have, there is an embedding into, let's call it y, because it's a bit like the Unida embedding. So y of A is this zero map. So this is how you embed A into ALX. And, and this embedding has a universal property, which is that suppose that E is additive and left exact, which means that it has kernel. Then for every additive functor here, additive, there exists an extension, let's say f prime, which is left exact, though, and essentially unique. Oh, yes, right. My notation are been changing, yes. Yeah. Okay, there are other ways to construct ALX, and Mike Prest this morning was giving another construction of the dual, maybe, which is right exact. But if you want to add co-kernel, you can take what Prest would call little mod A ab. Well, up. So you could take abelian presheaves on A of finite presentation. So that's what I mean here. So abelian presheaves of finite presentation.
That will give you kernels and co-kernels.
Oh, that would be the dual. Oh, okay. So, but it's very much okay. So that's another way of describing this construction. Okay. Now there is a little miracle, which is that suppose that you start with an additive category which has co-kernel. Suppose A has co-kernel. A has co-kernel. Then you do this construction, not knowing it has co-kernel. You treat it as an additive category, okay? So and so you have this completion. You add something. You add kernel to something having co-kernel. Well, the little miracle is that first that this has keep having co-kernel, and it's abelian. It's abelian. So that's the miracle. Because to be abelian means that there are relations between kernel and co-kernel, etc. And here you just do the Lex completion, not taking care of the fact that A has co-kernel, and not imposing abelian relation, but you do get something which is abelian. So in other words, this is abelian. And not only that, I mean, it's universal in the sense that now, if you take E an abelian category, and you take here a right exact functor, because you need to take care of that, right exact. Then the left exact extension will be exact. So it will be an exact functor between abelian category. So a consequence of that is that if you want to construct the abelian envelope of an additive category, so A is additive now. So you want to construct the abelian envelope, you first do, let's say, the right exact completion, which is just the dual of this thing, okay? And then you do the left exact completions of the right exact completion, and this is abelian, and the solution of the universal problem. I'm sure that you know this thing in one way or another, right? I think it was clear in your talk.
I knew it from Fry's paper.
Yeah. This is, the objects here, so you call them imaginary objects. Well, okay, yeah. Yeah. Because they are not modules over A, yeah, but you call them imaginary. So, so here you start with a functor which is additive.
No exactness.
No exactness, just additive. And here this, let me call it F double prime, is exact. It's an exact functor between abelian category. Of course, you could do the constructions the other way. I mean, you could take, now, if you do it this way, you go to A rex lex, or you could do it the lex and then A lex rex, and you get the same thing because of the the same thing. In other words, there's an isomorphism between the two things. So, therefore, there is a commutation operator between completing on the left and on the right, or a distributivity law or whatever. Something commutes. Now, what about AB5? So if there is an analogy between topos theory and abelian category, so AB5, abelian, AB5, so-called AB5 abelian categories.
Which is sometimes called a quadratic.
Okay, I will call it.
This morning it was called a quadratic.
Yes.
That's why I mentioned topo.
Now, if you work with Grothendieck abelian categories, they are really like toposes. And in this case, these results can be sort of improved, or maybe there is a version which, if you start with A left exact, maybe a right left exact category, and you take the Unida embedding, so pre-sheaves on it. That's the Unida embedding.
The additive version.
Yeah, that's the additive versions of the Unida embedding. Now, we know that this category is abelian because AB is abelian, okay? But in addition, it is also abelian, or Grothendieck abelian category, but it's the solutions of a universal problem. So, in other words, if E is a Grothendieck abelian category, and if you have a left exact functor f left exact, then you will have essentially unique co-continuous extension, which is exact. And co-continuous means that it preserves all coproducts, all sums, right? So if you look at this picture,
Subcategory of left exact functors.
what is a left exact?
On from A up to B.
Here it's an additive category with kernel,
Only kernel.
okay? And you consider an additive functor which preserves kernel.
Okay.
You don't ask it to be okay, and then you can extend it into an exact functor, which is co-continuous, right? Right. So because of that, you can easily construct the free Grothendieck abelian category generated by an additive category, right? And now there is this theorem of Gabriel and Popescu, right, which is going to say that any Grothendieck abelian category is a left exact localizations of that, and of course the left exact localizations are given by some Serre subcategory, and the Serre subcategory they play the roles of the topology in the abelian context, and everything just repeat. The whole theory of topos theory is completely, I mean, very, 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 almost statement by statement, you can find the analog statement. People should write a book, or maybe I should write one, where you make this parallel very, very strongly, because, yeah. Okay, now, but what else there is about abelian categories? Well, abelian categories, or actually additive category, can be tensored. You see, there is a notion of a functor additive in each variable. So you can create a monoidal category of presentable additive category if you want. And there's a nice tensor product in there. So where should I write this? Maybe I should. So let's say presentable additive categories. Presentable really just mean that you have collections of generator, essentially, and there is a tensor product between presentable additive categories. Tensor B. It's the solution of exhibiting a functor which is from A cross B. Let's call it theta, whatever. You want a functor which is additive in each variable, and that's it. I mean, that defines you what's the solution. And examples of a functor additive in each variable is precisely the Hom functor, for example. There are plenty of examples of functors additive in each variable. Okay. And there is a Hom AB is just the category of co-continuous additive functors. I mean, co-continuous. I mean, you want colimits to be preserved because we are working with presentable category where essentially everything is generated by colimits, okay? But there is also a subcategory of that, I mean, which consists of abelian categories. And it turns out that if A and B are abelian, then their tensor product as an additive category is abelian. So in this way, you can construct a closed monoidal two-category where you consider co-continuous functors which are also exact. Okay. And when you have a monoidal category like this, symmetric monoidal category, it's very tempting to look at a dualizable object. So when is it true that a Grothendieck abelian category has a dual in a sense that you have a pairing which will go into AB and a unit from AB to satisfying the usual identity for duality. And examples of that are given by the free one, the free over an additive category. So any of these if A is small, maybe I should write A is small additive. Then if you take the, let me take abelian presheaves. Presheave on A, abelian maybe. Okay. Then you can show, this is not difficult, that the dual, that this thing has a dual, which is abelian presheave on A op. So we have plenty of example of abelian categories that can be dualized, Grothendieck abelian categories that can be dualized. But the question is, what are they in general? I mean, so after hearing Mike Press this morning, I'm ready to make a conjecture. Is that there will be, if you take a small abelian category, this time, here A was just additive, and you put on it the topology that would say that every epimorphism is a cover. So that's going to be like looking for functors which from A up to AB, which are left exact I believe. So take any small abelian category and look at left exact functors from A up to AB. So I would conjecture, or a problem, I don't know. It's a bit like a guess, but so it could be wrong. Don't take it too, it's a problem. I mean, that these are exactly the dualizable Grothendieck abelian category. And the dual is what you think. It will be just the same description, but with A instead of A up. You have an opinion?
Well, it's true that the one direction is yes.
Which direction is yes?
Such categories will be dualizable.
Oh, that will be dualizable and etc. Okay. So it's an open problem. Okay. Now I want to go to another situation. If you take topos, you can generalize them in many ways. Maybe here you could put what could be called two rings. So these are a monoidal category with a tensor which is co-continuous in each variable and with a unit object. So here I should write set, and the unit object is, I mean, a co-continuous functor from set to E is it's enough to know it on the point, on the value on the point. So that's just an object of E. So, but these are, let's say, monoid in the category of presentable categories.
Symmetric monoid.
In the symmetric monoidal.
Symmetric monoid, yeah.
No, well, not for two rings. They are just okay. But the interesting thing would be that the two symmetric ring. Okay. So in this case, the tensor product is symmetric. And then you can specialize a bit further. Something I have been calling it a paratopos, because they are close to toposes. Okay. In this case, the tensor product is just a Cartesian product. So you have a Cartesian product. Well, you will have a Cartesian product in these categories too, but there is nothing that guarantees that the Cartesian product will have a right adjoint, an exponentiation. The exponentiation here do exist, but it's with respect to the tensor product. Okay, so here the condition is that this thing should preserve colimit in each variable. So in one variable is enough because the Cartesian product is commutative or symmetric. So so a paratopos, a small colimit, arbitrary.
No, but I mean,
Yeah.
necessarily filtering.
No. Okay. Now, why is this interesting? Well, first, a remark is that because of this condition here, a co-continuous functors between presentable categories always has a right adjoint. So these categories are Cartesian close. So in other words, if E is a paratopos, so implies that E is Cartesian close. And so there is an exponentiation which is right adjoint to taking product.
It's not locally Cartesian closed.
No, Cartesian close. Now, this, it's not difficult to show that a presentable category is a paratopos if and only if it is Cartesian close. It's a kind of character. To be Cartesian close is the necessary, I'm sorry. It's not what I wanted to say because what I just said is trivial. Because what I want to say is, disons, let's make it a theorem, but it's not difficult to prove. Okay. Okay. A presentable category is a paratopos if and only if let me call it this presentable category E. If and only if E is a localization of a pre-sheaf category, let's say set C set, C upset, a localization of a pre-sheaf category where the localization preserves finite product, in which the localization preserve finite product. So we have that C up set, and we have the localization functor, which is left adjoint to the inclusion, and it goes to E, and you ask that the localization functor preserve finite product. So in other words, paratopos are exactly like toposes, except that you replace the conditions of being left exact localization just by localization preserving finite products. And apart from that, the theories work completely parallel. See, in order to get this kind of localization, you need to exhibit a class of morphism that you want to invert. And what you ask is that this class should be closed under product, Cartesian product, not pullback, but just Cartesian product, and everything works. Okay. So there is a notion of geometric or algebraic morphism where the functor should preserve, should be co-continuous and preserve finite product instead of being left exact. But you just, yes?
Do you also take the empty product?
Yes, of course, yes. So there's always a terminal object in there, and the terminal object will be preserved by the morphism, right? Yeah. And all the big theorems about topos theory, I mean, just work. For example, you can decompose geometric morphism as localization preserving finite product, follow it by something which is conservative. You have everything just repeats itself. I mean, except that the kinds of category that you get is in some sense much weaker. So what is an example of that? And that's why I'm sort of interested in this subject. What is an example of a paratopos? Cat, the category of small categories. You know that this is Cartesian closed. It's easy to check that it is locally presentable. So that's an example of a paratopos. I can show you why it is a left exact localization of a pre-sheaf category. I can exhibit it. It's because if you look at simplicized set, the category of simplicized set. So this is the category of pre-sheaves on the category delta. Now, every simplicized set has a fundamental category. You see, there is an inclusion here, which is the nerve. Okay, and this nerve has a left adjoint, which is the fundamental category of a simplified set. And it's a theorem, which is not difficult to prove, that the fundamental category of the product is the product of the fundamental category.
Pi 1 is not a groupoid. Tau 1 is not.
Tau 1 is there is the pi 1. Pi 1 is the fundamental groupoid. If I use groupoid instead of simplified set, I will see that I will prove that the groupoid is a paratopos also, right? That's another example. So cat is an example, groupoid. Poset, you see, poset. Poset is a reflexive subcategory of cat. I mean, because a partially ordered set is actually a category. And there is a reflection functor. To every category, you can associate a poset in a kind of obvious way. You say that an object A is smaller or equal than an object B if there is an arrow from A to B. Yes?
What is the difference between a paratopos and a quasi-topos?
Oh. Yeah, a quasi-topos is something quite different.
Here you mean by poset pre-ordered set.
Partially ordered set. Partially ordered set.
No,
You have arrows in the two directions.
I'm sorry?
When you have arrows in the two directions,
it's pre-ordered, I think.
Here by partially PO set, partially ordered set, right? But it is a reflexive subcategory.
No, but this is
Question is whether when you have x smaller than y and y smaller than x, that is x
that's
equal
the
to y.
question.
Oh, yeah, sure. You have, but I can partially, so you want to a pre-ordered set, okay?
Yes, okay.
It's true too. You could put equivalence, the category of equivalence relations. And there are almost, this list can be extended in various directions because you have two cat, the category of two categories, three cat, okay, a double cat, double categories. Okay, I'm sorry?
All these considered as one category.
No. This is two cat. Oh, yeah, sure. We are in one category. Yeah, I'm not looking at two cells between two categories, right? I'm taking strict two cats and strict three cats and etc. And these categories, I mean, they are poorly understood. I mean, we understand what the topos is, the properties, and we would like to have an understanding of cat abstractly as a category. There are axioms that can be put there. The first, of course, is that it is Cartesian closed. There are other axioms that can be put, but what are the exactness properties of cat? I mean, we know, for example, that in a topos you can factor every morphism as a nice surjections and follow it by etc. We have all kind of, so it's a big question, and I don't know, except that let me observe that in many of these situations there is a factorization which is there are a couple of factorizations that are interesting. So let me just discuss one. Is that if you have a functor between two categories, then you can factor it as, for example, as a functor surjective on objects, let's say E, followed by a fully faithful monomorphism. Okay, that's one possible factorization. Okay, in other words, the inclusions of a full subcategory. Any functor can be factored in this way. And in a unique way. Essentially what you do is that you take the image of the objects of A, and you take the full subcategory generated by the image. But it looks like a bad factorization because this map looks bad. Okay, I don't know, but there is something and maybe interesting, which was observed by...
You can have bijective on objects.
There is another factorization, right. There is this Gabriel factorization where you ask for this map to be bijective on object and this one to be just fully faithful and you drop mono. But I'm choosing this one because, well, because I want to... there is a famous result by Dana Latch with another author. I forgot at the moment. I'm sorry. Apologize. Okay, which says that if you push out the push out of a fully faithful functor, the push out in cat. So if you have some fully faithful functor, it could be mono on object or not. It doesn't matter. It is also fully faithful. Now, what it seems to say is that cat. The opposite of cat is actually an exact category. See, in an exact category, you expect that the pullback of a surjection is a surjection. This is not true at all in cat, but the opposite of cat has this nice property, where the surjections now are played by fully faithful embedding. So I'm giving this as an example because I think that this kind of result should be true also in higher categories. In other words, the Latch theorem should be true also if you were to take infinity categories, where it's probably much harder to prove. So infinity one categories, that should be true also. So my understanding of cat is very poor. I only know that this is essentially Cartesian closed, that it has this kind of property. But it would be very nice if we could extend topos theory to this kind of category, possibly by adding a few axioms I think it's very much needed, given the importance of two cat, and their weak versions, infinity categories, infinity 1, and also for 2, etc. We should be able to extend topos theory to these categories. Okay, how much time?
You have 10 minutes. This is maybe, what about pseudo classifiers?
For cat?
Well, paratopos.
Sub-object classifiers? Oh, they are not there. That seems not that I know.
The main difference is topos.
Yeah, yeah. Okay, for the 10 minutes. Yeah, I would like to discuss with you pointed set. This is not a topos because the initial objects and the terminal object coincide. So the question is, if it's not a topos, what is it? Because especially with pointed spaces, you see, this plays a big role in topology, pointed spaces. And so abstractly, what is it? So I would like to make first an observation that there is, given a category, any category C, you can describe the category of families of objects of C. A family of objects of C is what you think it is. It's a family of objects of C. And a map between two families is also what you think it should be. Because what can you do to map this into this if you don't have any other information? First, you need to have a map from I to J. And for each I, you need to have a map from AI to B of phi I, or all I, in I. So a map between these two consists of a pair, F, and maybe, I don't know how to call it, F, bad notation. Yeah. Anyway, it's a pair, maybe capital. Oh, okay. It's a pair consisting of a map from I to J downstairs plus maybe a family phi I, okay, of maps like this. Yeah. Okay, so that's the, given a category C, you can construct the category of families of objects of C. Now, this is the coproduct completions of C. Fam C has coproduct. Arbitrary coproduct. And the idea is actually that this family is somehow a formal coproduct of the object AI. You should think of it as the coproduct of the AI. The coproduct are purely formal, so they may not exist in C. So I'm going to make sure that we know where we are. So I'm going to write a bracket here just for the inclusion. It's really like the unit functor. And actually, I'm looking, this is actually a subcategory of the pre-sheaf category. And I'm looking at coproduct of representables. Okay. So, this is free. This is, if you were to map C into a category with coproduct, you will be able to extend it along the unit embedding to a coproduct preserving functor from the family of C to C. Okay, so observation. If I take family of, let's say, set of pointed set, a family of pointed set. What is a family of pointed set? This is the same. This is a topos. This is the same as a covariant functor on a category which I'm going to describe like this: section, retraction, and here identity. So you take a category with two objects, and which I call 0 and 1, and SR is the identity with two arrows, generating arrows, and you just ask this equation. And if you have a functor from this to set, you will have two set, x0 and x1. You will have a retraction and a section. Okay? And of course, if you take the fiber of the retraction at a given point, then you get a pointed set, because the section is providing the base point of the fiber. So you get a pointed set, and in this way, you get a family of pointed set. Okay? And the converse can be done. So there is an equivalence of category between families of pointed set and pairs of sets equipped with two operators like this, satisfying this equation. And since this is a category of diagrams and sets, this is a topos. So that's the moral of the story, is that
chief of this two element category.
In fact, it's could be replaced by one.
How does it?
Even is one element just projector.
No, that's correct. No, sorry.
oh, yes, right. You could even have it with a projector. Yeah, that's true. Yeah. So definition. I have a name, but I'm not sure. A locus is a pointed, locally presentable category such that if you take family locus E, such that if you take family, the category of such that is a topos. I'm sorry?
Pointed means that it has it's pointed by the initial object or by what?
A pointed category, it means that the initial object and the terminal object coincide.
What do you mean by pointed category?
Exactly.
It means that the initial, for a presentable, is a locally is a presentable category.
Pointed category. What?
Oh, well, which name would you like me to use?
What's a pointed category?
It's a category where there are two notions, right? It means that first that the sets are pointed sets. That's one way. Or you could ask for a base point, for an object which is both initial and terminal. And there is a very close to equivalence between the two, right? Yeah. Okay. Okay, well, I would like to give you examples of locus. And this notion becomes interesting when we look at infinity topos, there is a notion of infinity locus, which is just the same, except that families here, by a family, an object here, I, maybe phi, I don't know. Normally, you would describe a family as a functor from the discrete category I to phi, okay? But in the context of infinity topos, I should not be discrete. I should be an infinity groupoid. That is a nomotopy type, right? This is but it makes sense. If you have an infinity category, you can consider families of object in it indexed by an infinity groupoid, actually by any Saint-Picel set, for example. It's a very, very standard notion in infinity category theory. So here maybe I should may underline this because we are no longer, for example, I could be given by a group. Then that would, it's a category with one object, but where the automorphisms are non-trivial. Let's give a group, and that would produce like an object in E equipped with an actions of that group. So, okay. And then, if you take the category of spaces.
But in that case, it's a topos.
I'm sorry?
In that case, it's a topos. If you have a group action, it's a topos.
This is for E, an arbitrary infinity one category, right? I'm not supposing that E is a topos, right? So now you could consider pointed spaces and families of pointed spaces, okay? Families in this sense, and this is again the same relation. As before. This relation shows that a family of pointed spaces, family in some extended sense, is actually the same thing as a map of spaces equipped with a section. Okay. Yeah, I will. 100 seconds. Okay. Okay. So what's interesting here is that there is a notion of a spectrum, of pre-spectrum, a pre-spectrum in topology is a sequence of spaces, x0, x1, etc., together with a map from the suspensions of xn to xn plus 1 for every n. And there is a category of pre-spectra. And it's very easy to verify that this is a locus. Well, actually, it's pointed spaces. Yeah, that this is a locus. In other words, you can augment this description with a base space, a variable base space, and this is suspension over B. So you have base space with sections, and I'm taking the pointwise suspension, and it's a pre-spectrum over B that you describe. And then the classical theory of pre-spectra is that pre-spect is that there is a functor to spectra. A spectrum, a pre-spectrum is a spectrum if the associated, the adjoint map from xn to omega of xn plus 1 is an equivalence. That's called sometimes an omega spectrum or etc. That's the idea of a spectra. It means that you have a sequence of space with a sequence of equivalence. Normally, what you have is a pre-spectrum, and then there is an associated associated spectrum. No, completely general. Now, the functor that takes a pre-spectrum to the associated spectra, there is an explicit construction, and this is a left exact. And you just by construction, it's a co-limit of iterated loop space, and it is a left exact. Pardon, I'm sorry?
Are you working in some infinity world or in the usual? That is, you are working in.
We are in the infinity world. Yes. Okay. But these two categories are pointed. They are pointed. And you can do this family construction. So you do family construction on both sides. So you consider families of spectra. And these are spectra over bases, where the base can vary. Okay? And so you see that the category of families of spectra is a left exact localizations of this category. But this category is a topos. Okay? It's a topos. Because of this kind of construction here, because of this kind of dictionary, you can, it's not difficult to show that the categories of families of pre-spectra is a topos. And therefore, the categories of families of spectra form a topos. Okay? Now, this is something which was observed by various people. I first learned it from Georg Biedermann in 2007. And Charles Rex observed it too, about the same time. And it was coming from a good Willy calculus. But the proof that I am making here is completely elementary in some sense, because it does not use good Willy calculus. It's completely standard, almost standard construction. And the fantastic thing about this, look, the stable category of spectra is very far from being a topos, very far. Well, maybe some people will say it's very close because it's like an abelian category. It looks like a topos too. But if you just take families of spectra, bundles of spectra, okay, there is a bundles of spectra where the morphism are, what you think they should be. Okay, a morphism is a map, a continuous map between the base, such that if you pull back E prime, there will be a map over the pullback. Okay, so F star of E prime. This is this category of parameterized spectra has been studied by Peter May, for example. There is even a book about this, right? But they have not observed that this is a topos. Well, at that time, topos, infinite topos didn't existed really. But it seems to indicate that one could embed the theory of stable categories in topos theory. That I don't know if this embedding is useful, but I would conjecture that if you take an infinity one stable category, that if you take families, exactly the same constructions, families of object in this, it has to be co-complete, so you need to have co-product, and I mean the category of spectra of stable category that you're looking at. Then if you do this construction, that you do get a topos every time. including the case of chain complexes. I'm looking at Maxime. This may be a wild conjecture, and that's why Maxime can, or maybe he is just polite. So if I had time, I would provide some argument supporting it, but I don't have time. Okay, so thank you.